Hello and welcome. My name is Ian, and in this video, I will be talking about experimental error and the famous Gaussian or normal distribution. So when we're doing an experiment, we produce error. So when we report measurements, we want to include how certain we are about those measurements. And that usually comes in the form of an uncertainty or error statement. And another name for this is a confidence interval. And usually this corresponds to the standard deviation of a Gaussian distribution. So for example, let's say we're looking at this bolt here. We're measuring the length with a ruler, and we want to report the length that we measured. So we get it's 15.1. And the ruler we know has a standard deviation, a Gaussian standard deviation or a Gaussian error of 0.6 centimeters. So we would report that the length is 15.1 plus or minus 0.6 centimeters. And this is for a situation when we know the value of the precision, or we know the value of the error. So this applies to mostly things where maybe like the instrument manufacturer or the device that you're using has a reported value that allows you to have an uncertainty that's not based on the measurements you've taken. So it's independently reported. So for example, a mass balance might have a known precision or a known error of 0.01 grams. And so this is in effect saying that when I take a measurement, the expected value or the population like true mean, if I were to repeat this measurement many times, it would approach the value mu. And if I take one measurement, then that measurement I get is within one standard deviation of that true mean, and then that standard deviation is 0.01 grams. So this means it's important for us to understand the distribution that gives rise to these precision statements. And this is the normal distribution. So you can see here the equation written out. The normal distribution or the Gaussian distribution. This is a type of continuous probability distribution. It's the most useful because it's the one that we use to describe error. And it's also useful because it's often there are other distributions that at large numbers. So for example, the binomial distribution when n is extremely large, it starts out very blocky, right? But if we add huge numbers to it, for example, we do 112 dice throws instead of just 2, for example, or we do 1 million dice throws, then that smoothness starts to approach the normal distribution or the Gaussian distribution. And a similar thing happens with the Poisson distribution when lambda, or this average number of events or intensity value, when this gets really large as well. So let's take a look here at the normal distribution. So we have these different parameters, right? We have mu here, so that's going to be our population mean. So this is one of the parameters that we need in order to solve for the probability at any given x value. So that's our independent variable here. And then the other parameter we need here is sigma, or the standard deviation. And then if we have these things, we right off the bat also know these quantities like we do with the binomial distribution, except in this case, they're a bit obvious. So the expected value, or the population mean, is going to be defined as mu. So basically, this is kind of a tautology, right? We're parameterizing it with the mean. So obviously, the mean is going to be the mean. And a similar thing happens with the variance. So the other parameter for this distribution is the standard deviation. So these statements are a bit very simple. But if we take a look at the distribution here, It's, of course, this classic bell curve. And if we kind of analyze it a bit, we learn some interesting things. So the first of these is that the standard deviation, if we're one standard deviation away from the mean, this is interestingly the inflection point. So the point at which the slope changes from becoming steeper to becoming less steep. Or if you're on this side of the curve, from getting more steep to less steep. And we can start to think about these areas. So if we remember, for continuous probability distributions, we think in terms of ranges. So a probability is 0 for any one point x value on a continuous distribution. But if we think in terms of ranges, then we can think about the area as corresponding to a probability. So in the case of the Gaussian distribution, the area that is contained within -1 standard deviation and +1 standard deviation away from the mean, this corresponds to 68.27% of the area of the total distribution. And this is another way of saying that 68.27% of points sampled from this distribution are going to fall within 1 standard deviation away from the mean. If we go out a bit more, so if we go out to 2 standard deviations, so -2 to the left and +2 to the right, then this is going to correspond to 95.45% of the area under the curve. Or in other words, this is 95.45 probability that a point lies within 2 standard deviations of the mean. And we can keep going. So this distribution just keeps going out, but it also keeps getting smaller and smaller. And so when we go out to 3 standard deviations, we're already up to 99.73% of the area. So more than 99% of points are going to lie within 3 standard deviations. And so we can use this way of thinking to understand errors and Gaussian distributions. So thinking in terms of integer numbers of standard deviations away from the mean. And one way that this is done is with something called the z-score, z-score. And it has this definition here, right? It's x minus mu divided by sigma. And the way to think of it is it's just an integer representing number of standard deviations away from the mean that you are. So if z is 1, then you're 1 standard deviation from the mean. And so this curve here is what's called the unit Gaussian. And the unit Gaussian is a way for us to connect standard deviations with probabilities. So you have tables here, for example. So this is the 2-tailed Gaussian integral table. And what we're looking here is we have the areas under the curve and how many standard deviations they correspond to. So we have z or z here on this left column, and then these all correspond to particular areas. So we can look up, we can see that 1 standard deviation away corresponds to 68.27 probability. And that's exactly what we said over here, right? That 1 standard deviation away corresponds to 68.27% of the area. And this is can be useful. So for example, we can consider like a fitting problem, right? Where we have some points and we're fitting a line to that point. And each of these points, we've applied error bars, right? And these error bars, they're standard deviations. So we're using the standard deviation for these error bars. Okay, well, if it's a standard deviation and a good fit, should be robust to noise, or rather, we're accepting that there's random noise in this data, and that the fit is corresponding to, say, the mean that's passing through each of these points. Well, if that's the case, and if this data is actually Gaussian distributed or normally distributed, and these are indeed standard deviation error bars, then we should have a situation where 68% of these error bars intersect the line that we fit to this set of data. And the remaining, about 1/3 of them, should actually not touch the line. And this could give you an indication of how well your data has been fit. If it passes through more than 2/3 of the data, or 68%, then maybe it's an indication that you've overfit your data, or that the noise is not exactly following a normal distribution like you were assuming. So that's just an interesting tidbit. If we look, then we can keep checking out this table here. So 2, we said earlier, corresponds to 95.45 probability. So we can see that here. But we could also look this up for an arbitrary value. So if we want to know, what is 95% probability, for example, not 95.45. Well, we can see here that if we look up the way you read this table is you add the number up here to the number on the left. So that occurs at 1.96 here, standard deviations, or Z of 1.96. And that's what you need if you want 95%. And this is useful for confidence intervals. So you might often see a confidence statement given in terms of 95%. So we might, instead of talking in terms of standard deviation, we might want to say, this statement is true with 95% probability. And in that case, we would want to use 1.96 standard deviations as our benchmark there. And so this is for two-tailed integrals. And so in this case, these values correspond to the area occurring between these two tails here, and then the remainder, 5% in this case, that's divided equally among the two tails. But we could also consider a one-tailed argument. So what is the probability that my point lies anywhere up to a particular point? So we have one tail in that case. So a 95 confidence interval could be said in this case. And then this would be, instead of, so this then would be saying that a point lies within this area, or this probability below a particular point, say 2 standard deviations away. So let's give an example here for a confidence interval. So we have a tube filled by a pipetting robot, and this is extruding a volume of 52 microliters. And we have a known precision, a known standard deviation of 1 microliter. So if we look up in the Gaussian table, we see that 68% of the volume lies within 51 and 53 microliters. So how did we get that? Well, we know that standard deviation is 1 microliter here. And here I've just kind of rounded it a bit, so it actually should be 68.27, but that is our corresponding probability for 1 standard deviation, which we know is 1 microliter. So a confidence statement could take the form of, for example, the true volume is within 51 and 53 microliters. And this statement would be correct 68% of the time. That's another way we could say that. Or we could state this as, we make the statement with 68% confidence. So that's for 1 standard deviation. Now, oftentimes you'll see 95% confidence statements. So we might say we have a 95% confidence interval for the volume being located between 50 and 54 microliters. Depending on how precise the statement is, you might either use 1.96 sigma, as we said earlier was 95, or often 2 sigma, 2 standard deviations is used in that case. So we could approximate the 95% value with just 2 times our standard deviation, or 2 microliters here. So I've just taken the measurement here. So we measured 52. And then just subtracted 2 microliters and added 2 microliters to get that interval for 95%. So let's go back, take a step back and think philosophically again. So why do we use the Gaussian distribution in the first place? And what is it that makes error follow a Gaussian distribution? And so the short answer to this is that Gaussian distributions can be used to describe the cumulative effect of many independent variables. So what do we mean by this? So let's say we have a bolt here and we want to measure the length. What are all of the possible sources of error, or what are all the ways that we could be slightly off in this measurement? So we can imagine one of these sources of error might be simply the calibration, the manufacturer's quality of this ruler. But there are also things like maybe the angle of the bolt that we've chosen might not be quite accurate. Our visual judgment of the line marker might be off a bit. And there's sort of a kind of infinite number of like tiny little sources of error maybe that could contribute to us being closer or further away from the true kind of theoretical or ideal measurement of this object. And if we were to kind of represent this on, say, like a little number line here, where mu here, that's our population mean, or sort of the true value existing here. And if we add the contribution of different sources of error, so maybe placement error could cause us to be a little bit off in the negative direction. But then visual judgment, maybe we're off in the positive direction, another arbitrary amount is not exactly equal, or in any way related to the placement error, but it's acting in another direction. Maybe we have an angle error and that's acting again in the negative direction, and so on. So we have all these sources of tiny variation, and we add them all up, and then that's what's going to give us our final measurement value. It's going to be the cumulative sum of all these little independent errors. And so what this is essentially a random walk, like a 1D random walk. And if we take, say, a second measurement, maybe all of these errors are going to act in different directions. They're going to be kind of reset and shuffled, and we're not going to get the same value. We're instead, sampling from a different collection of these variables all acting independently. And when you do this, the central limit theorem kicks in. And basically, this is the idea that anytime you have a process like this, a set of independent random variables, and you're just adding them together, then this is going to approach a Gaussian, or this is, you could say, the generating process behind a Gaussian distribution, in the same way that we replicated the generating process behind the binomial distribution when we did this dice enumeration example. Let's take a look then at some code that shows this. Okay, so here we have the sum of several independently chosen random numbers. So we have a for loop here, and then this is simply just going to generate a random number between -1 and +1, and sum this up depending on how many we've told the program to generate. So in the first case here, we ask it to just pick one of these numbers. And then we repeat this for a large number of rounds. So we do 100,000 of these measurements. Okay, and then there's no reason for this to obey any trend other than this uniform random distribution here, right? We're just picking random numbers between -1 and +1. So there's no reason at all for some sort of trend to emerge here. If it's truly equally probable that we get, -1.3 versus +0.1, we're going to get something like this, just evenly distributed from -1 to 1. But the moment we add another variable in there, so here we're taking 3 of these, we're picking 3 random numbers, and we're summing them together. So here we have some variable, and then again, we're repeating this. So we're doing this 100,000 times. But the moment we do this, we start summing these variables together. Now we get this distribution emerging. So now it's going to span the range from -3 to +3, right? The max we can get if we roll, say, +1 3 times in a row, or a -1 3 times in a row. And okay, here it's continuous, right? We can pick any value, but I binned the data. So it's similar to the dice example, except that we can get an infinite number of values from -1 to 1. But we binned the values, and so you can see how they're distributed. And what we've generated here is a sampled, noisy, in this case, normal distribution or Gaussian distribution. And this is the central limit theorem that is causing this to happen. And this is the generating mechanism behind the Gaussian distribution in the first place. And it's what normally happens when you measure things, that you have independent sources of error all contributing and adding up with each other. So that's why this is an extremely useful distribution to know about. So let's look at the idea of taking multiple measurements. Okay, so we talked about what's a confidence statement if we take one measurement using a machine where we have like a reported standard deviation or reported precision for that machine. And so that confidence statement looked like this, right? So we said the population mean, the true value, we're with 68% confidence, we believe is located at X, that it lies within one standard deviation, it lies within this range, -1 standard deviation plus standard deviation, and that is true 68% of the time. And so that's the case for a single data point with a known standard deviation. But let's consider, what if we have multiple data points, as one often does, and instead of reporting a single measurement, we're reporting a mean. And of course, if we take multiple measurements, then we're going to be more certain about the mean. If I take millions of measurements versus 2 measurements, then I will be able to have much more confidence that the mean is what I say it is here. And intuitively, then our confidence statement should reflect that. So this plus or minus value that we're tacking on here, if we just use the old standard deviation, the reported precision of the machine, this is not going to adapt to or reflect the fact that we've made more measurements and that actually we're much more confident about this mean. So instead, what we can use is the standard error of the mean. And so here I've indicated this, denoted this with a subscript X bar here. So let's take a look at this. So what is this exactly? If we were to take the mean of the mean, so the mean is in fact a random variable itself. So just as X is a random variable, X bar itself is also a random variable. So if I take a sample, I take 10 measurements, I compute the mean, that has a value. I repeat the experiment, I take 10 more measurements, I take a new mean, that will have a different value. So X bar itself is a random variable. It's subject to fluctuation. And it's described by a probability distribution. And that probability distribution, so here we're kind of drawing it, that probability distribution is going to be narrower or broader depending on n. So here I've tried to draw, so if we have a large n here, the red curve, the distribution has a thinner waist here. The variation is less, the spread is less of this. And that is reflecting the increased confidence that we have in the mean. So if we're going to report our confidence, we want the interval that corresponds to this distribution of X bar itself, and not just the distribution of X. And so this gives us that's what we have with the standard error of mean. So it's going to be defined as the X's sigma or X's standard deviation, but we're dividing by the square root of the number of measurements that we've taken. So the more measurements we take, the smaller actually this value becomes. Yeah, so let's consider an example. So we have an experiment. We take multiple measurements, and each experiment consists of taking 10 samples, 10 measurements, and we're computing the standard deviation, and we get a value for X bar here. And if you look down here, X bar, these values are similar to each other, right? 1.442, 1.445. But in this second group down here, they're varying a lot less, right? X bar is 1.443, 1.442, but here it's going all the way up to 1.613, 1.992, 1.296. So what's happening? X bar is not varying as much in this case. So it's got a narrower spread. And what happened was we changed the sample number. So instead of each experiment consisting of 10 measurements, it consists of 10,000 measurements in the second group here. And then what we see then is that the spread of X bar is much less. It's more tightly distributed around, something like 1.44 something. And our variation has been pushed out to this third decimal place here. Whereas in the case where there's only 10 measurements, it's bouncing around all over the place, 1.6, 1.2. And that's because n is larger. So this is an important thing to think about. So let's consider like some different scenarios. Let's say we have a data set and we take 40 measurements. And in a situation where the spread of X, our original random variable, is large, so here we have sigma is large, the standard error of the mean, our uncertainty with regards to our sample mean that we compute, is going to be really high because the spread is large and we didn't take that many measurements. So we're going to be sort of maximally uncertain about our mean value that we get here. But let's say we have that same distribution. It has a large spread like this, but then we take 10,000 measurements. Okay, so even though the spread is the same here, the spread is really large. Now my confidence around X bar has increased. Like you can see also visually, like we're much more certain that, the mean is going to lie here, even though it's very spread out. The mean is, we're relatively sure. And then on the flip side, consider a more tightly distributed original distribution. So X has a small standard deviation. And in this case, if we take 40 measurements, we're definitely more confident that X bar, lies within this range here than we were in the case when it was a really spread distribution. And if we sort of combine these, so we have both small n, a small standard deviation and a really large number of measurements, then this is sort of the best of both worlds. So now we're extremely certain that X bar is here. And it's because both that the distribution itself is really tightly distributed, but also because we took 10,000 measurements, so we're much more certain about it. And we have a stronger confidence statement as a result. So let's give an example. So standard error, mean confidence intervals. Consider a flow cytometry experiment, and we're measuring the scattering signal for 5,000 different cells. And the fluorescence level, the mean that we get from our measurement is 72. So we take a measurement, 72. And this was from 5,000 different cells, 5,000 measurements. We already know the instrument's precision. So for one of these measurements, we know that this is 40, intensity units. And we want to know what's the 95% confidence limit on our estimate of the true mean fluorescence, the population mean. And so what we can do then is produce a confidence interval statement that utilizes both our mean and our standard error of the mean to represent our confidence. So the mean we already know, it's 72. The standard deviation is 40, we know, and that's just for one measurement, right? but we took 5,000, n is 5,000, so we can compute the SEM here, standard error of the mean, and that's going to be the standard deviation of 40 divided by the square root of n, or the number of measurements. And so that's going to be 0.5656. So if we want to construct a 95% confidence interval, we can recall from the Gaussian table that 95% corresponds to 1.96 standard deviations away from the mean. But in this case, now we're going to use the standard error of the mean for this statement. So if we want a 95% confidence statement, then it's going to be 1.96 times this thing here, 0.5656. So that's 1.11. So we can word this in the following way. So we say the true value, the population mean, it lies between 70.89. So I'm subtracting this from our 72 and 73.11. So that's our 72 plus this value here. And since that's 1.96 sigma from the table, we know that this is going to be true 95% of the time. In 95% of universes, this statement is correct. That mu lies between here. Okay, so that's Gaussian error. But let's say we have an experiment where we're calculating something or computing something based on measured values. So a good example of this might be concentration, and we're using the Beer-Lambert law to estimate concentration. And the Beer-Lambert law is a function of absorbance and path length, and then you have some parameter, the extinction coefficient. And so this one is going to be constant, but then we have these two measured quantities here. So we have a path length, and that's going to be subject to its own error, sigma L. And then we have an absorbance measurement that's based on our detection apparatus, and that's going to have its own error, sigma A. And so these are measured quantities, and we have already known information about these error values. But what we want is the uncertainty of the concentration. So we measured these things, and now we want to make a confidence statement about C. So we calculate C using this equation, but how certain are we? What's the 95% confidence interval for that calculated value? So this brings us to the combination of error method. Now, this is sometimes called law of combination of errors. And this applies to anytime you have a function of variables that are subject to error. And so we have this function here, say f, x, y, z, just like we did for the concentration in Beer's law. And then we have values of, say, sigma x, sigma y, or sigma z here. So the error of this function of f is going to be given by this equation here. And what this is saying is that we're going to take the partial derivative of this function with respect to, in this case, x, and then here y, and then here z. And then we're multiplying that. So we're taking that quantity squared and multiplying it with the known precision or standard deviations for these respective variables squared each. And if we do that, then that's going to give us the square of our standard deviation or our error for this calculated value, the function value. And then so if we want the value itself, then we take the square root. So we have this equation then basically that's going to give us our error for this equation, for this function. So here's an example. So let's say our function is 3x. So then we could compute, fill this out. So we take the partial derivative of 3x with respect to x, and we square it. We multiply by sigma x squared here, and we take the square root. And then that would then give us, if we simplify this here, that then gives us the error for f of x here. So in this case, it's just 3 times sigma x. if we have, let's say we have a dilution pipetting experiment here, and we have a volume and a concentration, and we have a final mixture that's given by this equation here. And then what we want to be able to say is what is the confidence that we have in that concentration. And so then in this case, we have experimental air that's introduced in the volume. So we have, we've used the pipette to measure, or we know that there's some air in the volume that is associated with the pipette. And then let's say we've also used a spectrophotometer to check the concentration. So we have an error associated with concentration. And what we want to know is what's the calculated concentration after this dilution. So we have these different volumes, we have this concentration. So we want to be able to produce this confidence interval statement here, that the true concentration after the dilution lies within some range. So here our equation then is going to be made up of these volume concentration variables. And for simplicity, we can just replace them with x, y, and z here. And then we apply our formula, right? So we're going to take these partial derivatives and these apply these squares. So the partial derivative of this equation here, xy over x plus z with respect to x, if we solve that, that gives us this, yz over x plus z quantity squared. We do the same for y and z. And then this gives us everything we need then to evaluate this expression. So we remember it's going to be, it's up here. So we want the square root of this whole quantity. And then it's each of these partial derivatives substituted in here. And if we solve for everything, simplify it, then we are able then to compute the uncertainty for this function, even though we didn't measure it directly. Okay, and then for variables that are correlated, you can add another term here that utilizes the correlation function that we learned about in previous video. And then that's going to allow you to compute this even when you don't have independent variables. So to summarize, if we're working with measurement error, we're going to be trying to report our confidence. And the way we usually do this is assume that the error is following a Gaussian distribution. And the reason this is usually valid is because the generating mechanism for the Gaussian distribution is very similar to the process that generates random errors. In other words, it's the sum of independent random variables, and this is the central limit theorem, basically, that that says this is the case, that this is that you are going to get a Gaussian distribution when you sum these variables. When you're doing multiple measurements, you're taking the mean, and the mean itself is a more confident statement than a single measurement. So then it makes sense to use the standard error of the mean, which is going to be a version of error or standard deviation, but one which depends on the number of samples that you took. And then finally, we have this combination of errors method, and you're going to use this whenever you have an equation that is giving you a computed value based on measured values. And those measured values have their own errors associated with them, and those are going to propagate through and influence your calculated value and create a new corresponding error for that. So that's all I had, and thank you.